Okay. Actually, most people already met Fran Bagenal over there, but let me formally introduce our guest speaker this evening. Dr. Fran Bagenal is a research scientist and professor at the University of Colorado, Boulder, and is co-investigator and team leader of the plasma investigation on NASA's New Horizon mission to Pluto, and the Juno mission to Jupiter. Her main area of expertise is the study of charged particles trapped in planetary magnetic fields and the interaction of plasma with the atmospheres of the planetary objects, particularly in the outer solar system. She edited the monograph called Jupiter, Planet, Satellites, and Magnetosphere, published by Cambridge University Press in 2004. Dr. Bagenal was born and raised in the UK, received her bachelor's degree in physics and geophysics from the University of Lancaster, England, and her doctoral degree in Earth and Planetary Sciences from MIT in 1981. She spent 5 years as a postdoctoral researcher at Imperial College London before returning to the United States for research and faculty positions in Boulder, Colorado. She has participated in several of NASA's planetary exploration missions, including Voyager 1, Voyager 2, Galileo, Deep Space One, New Horizon, and the Juno mission, which she's going to talk about this evening. Please, Dr. Bagenal, proceed with your presentation.
Okay, what do you want to do about the sound? You want me to use the microphone?
Yeah.
Okay, sure, no problem.
It doesn't come together anymore.
Right here too, just so the mic picture.
Yeah, that seems awful. Toby,
Oh, you think the sound will be better if it's closer, is that?
Yeah, this is kind of your main sound source.
Okay. Okay.
all right.
Okay, hang on.
Let us know online if the sound's so quiet.
Okay, how is this looking? Let me do full screen. Okay, great. Okay. So it's a great pleasure to be here for the and meet with you again. It's been several years since I visited with Das. Always a pleasure. Interesting that you said that you're celebrating your 75th this year, because the Laboratory for Atmospheric and Space Physics at the University of Colorado, where I work, is also celebrating its 75th anniversary. It got heavily involved with exploring space, first of all with rockets left over from the Second World War, and using them to take up UV instruments to look at the Earth's atmosphere, to look at the sun, and so on, and has been now sent UV instruments to every planet except Pluto, I'm afraid to say. That was the SWIRI instrument that went to Pluto. Okay, so I want to talk about the Juno mission, which has been orbiting Jupiter since 2016. And I want to give you an update on what we've been seeing since. But to do that, I want to start off with a basic Jupiter 101 and tell you a little bit about Jupiter. Obviously, it's very big, 11 times the size of the Earth, 318 times the mass. It orbits out at 5 times the distance every 12 years. And if you map it out, you can see these classic belts and zones, stripes across, as well as the Great Red Spot. Now, when we think about the atmosphere, we have to think about what we're looking at. And what we're looking at is a layer of clouds. And the top layer of clouds is not too different, the pressure level, than our surface here on Earth at 1 atmospheric pressure. And but you have to realize that most of the atmosphere, 99%, is hydrogen and helium, but we have these layers of clouds, ammonia at the top, mixture of ammonia and sulfur, ammonium hydrosulfide in the middle, and then we believe there's a water layer deeper down. Now, when we look at these clouds of Jupiter, we don't really know why it's colored, and we'll come back to this topic a bit later. The white clouds are ammonia, fresh ammonia, but then there seems to be this coloring, and that's been a big question. Now, why we're interested in Jupiter is because it's sort of archetype of gas giant, and it's important to understand what's inside Jupiter because it tells us about the formation of our solar system, where we believe that a young sun was formed. There was this big disk of material orbiting around this young sun. And of course, it was hotter closer in and cooler further out. And so then we have rocks and metals condensing in closer to this young sun. So we get Mercury, Venus, Earth, and Mars made out of rock and metal. And then further out, if we go further beyond the frost line, you get ices such as water ice and so on that formed condensed with that rock and metal, but there's a lot more of water than there is of those metals. And then the gas giants formed beyond this frost line with cores of ice, which then captured the hydrogen to make these gas giants. Now, what we want to do with Juno is to go and look at Jupiter and work out what it's like inside, what's going on with the clouds, what's going on with the radiation belts, what's going on with the magnetic fields. And we use this spacecraft, which you can see, there's a human down here on the left. For scale, this would barely fit within this room, the spacecraft in here. It has a bunch of instruments on it. It's obviously the solar panels are powering it with about 500 watts of power out at Jupiter, and it's spinning every 30 seconds, trying to keep the solar panels pointed to the sun. And at the same time, the communication is done by the antenna, which also does gravity science. I'll explain why and how in a minute. And then we have various instruments, magnetometer, charged particles, antennas for the waves. And then we have various spectrometers, microwaves, which I'll tell you about. It's very important for measuring the interior. We use infrared spectrometer that was built in Italy, a UV instrument, and a little camera. And I'll tell you the specialty about the little camera in a bit too. So we have to be careful when we go to Jupiter because there are trapped MEV, very energetic electrons that are trapped in the magnetic field. We've known about this since the 60s, and the magnetic field wobbles around. It's tilted by about 10 degrees, just like Earth's magnetic field is tilted by about 10 degrees. And so you see these radiation belts trapped in the magnetic field wobbling about when you look at it from Earth every 10-hour rotation. So we have to avoid those radiation belts. So we designed an orbit that would fly over the clouds and under the radiation belts and avoid these radiation belts. But what happens, because Jupiter is mostly fluid, as it spins around, it's fatter at the equator than the poles. And so this causes the orbit to evolve. So we have orbit 1 here, 16 and 31, showing you how this orbit evolves with time. And so eventually the spacecraft will go into these radiation belts. Now, it only takes 2 hours to go from pole to pole, but it takes many days to complete its orbit further away. And we're trying to work out by flying over these clouds and looking through them to understand what's going on inside. So I was lucky enough to go to Lockheed Martin down here in South Denver, where the spacecraft was being put together. I got all dressed up in the bunny suit and kept my hands to myself because I'm not an engineer and I didn't want to touch anything. But I could look around and you can see this is the spacecraft being put together. This big panel is where the microwave is going, and then they're putting all the electronics in the back. It's just amazing what they do to make this spacecraft. And so then here are the solar panels. They stretch out, they're being tested, and then they get folded in. The whole thing gets flown out to Cape Canaveral. We take a picture, a selfie. We slap stickers on the rocket, and then we take a selfie, and off it goes. So it was launched on the 5th of August, it says here, but in JPL, where we were all watching, it was, this is the 5th of August, sorry, of 2011. That's right. It was launched, went out, we did a maneuver, came back to the Earth to get a gravity assist, and then headed out to Jupiter. And then that's where we were at JPL waiting for its orbit insertion on what it says the July 5th, but at JPL, of course, it was July 4th. We were all excited. So this is important. Can we turn off these lights, please? Because I really want you to see this. This is not a simulation. This is a real movie. I'm sorry, I really think it's worth us trying to turn these on. Yes. Okay, perfect. I'm just going to go back, actually. I'm going to go back and do it again. Okay, so this is a movie. It is not a computer simulation. This is a real movie. Okay, so we're approaching Jupiter and we're making a movie. The sun is off on the right. Okay, and 40 minutes later, the photons hit Jupiter, bounce off Jupiter, and come into the eyes of the camera on Juno that is looking at the system. And you see the moons orbiting Jupiter. And so you see them going into the shadow behind. Boom, out, in it goes, out it comes. And then you can see Io is the closer, then Europa, then Ganymede. Io, Europa, and Ganymede are in resonance orbits. So this is amazing view. We don't get this view from Earth because obviously we're seeing this as not day and night. It's a continuous observation, right? Can you imagine how Galileo would have been so excited to see this? Amazing, isn't it? Right, these Galilean moons. Come on, Callisto, catch up. You can do it. Okay. Anyway, that was an amazing picture we took on approach. The first orbits were 53-day orbits, going out to 100 Jovian radii further away and in close, wrapping over the poles, and then takes a long time, send the data back, plan for the next orbit, and so on. We've now shortened them to 32-day orbits, and we're actually now have made 62 flybys. Actually, the next flight, the 62nd one, is going to be later this week. Okay, so we're doing all of these flybys one after another now. I'll get back to that in a minute. So let's think about what we're trying to do. We're trying to understand what it's like inside Jupiter. And this is from a textbook that describes the standard view where you have rock, a core of rock and metals and hydrogen compounds at the middle. And that's very dense, denser than all the metals that you can think of, and is several times the size of the Earth. Then beyond that, you have hydrogen, and up near the top, it's very low density. So density on the right here, the density of water is about 1. Okay, so that's easy to remember. And so then density of rock is down in here and metal down in here. So the density is fairly easy to understand. And what happens is, as the density and pressure increases, hydrogen changes its nature from molecular to atomic to metallic hydrogen. I'll come back to what that means. The temperature increases And you can see it's quite cold at the surface, but near the center, it's several times, about 5 times the temperature of the surface of the sun. So it's hot deep down. And then we've got pressure, which is 1 atmospheric pressure up here and gets down to 100 million times that. So what do these pressures mean? Okay, well, let me talk this through. If you are, people at home are going to miss the dance. Okay, so if you think of pressure through my feet, you've got my mass coming through my feet, mass through the area of my feet, mass per square area, so it's pressure. Now, what happens to that pressure if I lift up 1 foot? What happens to the pressure of the other foot?
Doubles.
It doubles, right? Half the area, same amount of mass going through. Okay, but to get the pressure that's in this room that we are breathing, 1 atmospheric pressure, how does that compare with the pressure through my feet? Well, it turns out you need to have 7 people on my shoulders, and all of that weight through my feet would be equivalent to the pressure in this room. Now, it doesn't feel like that because we're so used to it. Okay, we breathe this all the time, but you can check my math, as people have, and it's correct. Okay. So, sorry, I've got to get rid of this. So what do these pressures mean at Jupiter? Well, what you need at Jupiter is not lots of humans, but you need 1,000 elephants standing on top of each other's shoulders with the bottom elephant standing on 1 foot on a stiletto heel, okay? To be equivalent to the pressure we're talking about at the center of Jupiter. And it's important to talk about this because these pressures are, first of all, they're not something that we've ever measured in the lab. Nobody has gone to NSF and said, can I have 1,000 elephants and do this experiment? We don't actually have the technology to do it otherwise. But it also, we don't know how hydrogen behaves at these pressures. Even the nuclear labs have not worked out how hydrogen behaves. So this is a good question. We want to measure the pressure, we want to measure the distribution of mass and understand what it's like inside. So we think that the stuff that Jupiter's made of is pretty much the same as the sun because it came from the same nebula cloud that the sun was formed from. But the question is, how is it distributed inside? Do you have, like the textbooks have, these solid layers, a core, a mantle, a top, or is it all mixed up? And that's one of the things we wanted to learn. So what we do is the spacecraft goes by Jupiter, sends a signal to the Earth, and we measure the radio signal, we measure the Doppler shift, the shift in the frequency due to the mass distribution inside. So if the spacecraft is wiggling about because of the distribution of mass inside Jupiter, then we'll have a variation in that Doppler shift. And so we can measure the distribution of mass inside from the Doppler shift of the signal that we send back to the Earth. This technique is used in various other planets as very important for understanding the gravity and distribution of mass of planets. So what we found is that indeed, it's not like the textbooks say, there isn't a distinct separate core. The heavy elements seem to be mixed up with the hydrogen. We have helium raining out. Helium is about 4% of the cosmic abundance of elements. And then all these boundaries seem to be fuzzy. The stuff is all mixed up. It's not as simple as we thought. So what's going on inside with this metallic hydrogen? Well, somewhere about 80 to 90% of the radius, we think now from Juno it's closer to 90% of the radius, the pressure is high enough that hydrogen changes from a molecular state. So the molecular hydrogen is 2 protons and 2 electrons going around each other. And what happens is when you get the pressure really high, those protons and electrons can move separately to each other. And so that then means that you can drive an electrical current. So the positive electrons go one way, positive protons go one way, and the negative electrons go the other way. And so you end up with a current, okay? And so you can drive electrical currents inside, and the ingredients you need for a dynamo, a generator magnetic field, is that you have a little bit of spin, you have internal heat that drives convection, turning over this metallic material that is electrically conducting. And indeed, Jupiter has a very strong magnetic field and dynamo. So if you think of the Earth's magnetic field as like a bar magnet tilted by about 10 to 11 degrees, and the magnetic fields come out the southern hemisphere and into the north. And of course, you probably know that the Earth's magnetic field flips sort of every 200,000 years or so. The sun's magnetic field is in the process of flipping. Every 11 years it flips. That's why we've got all this aurora right now, because it's in the process of flipping, and that's when it gets very active, sending out coronal mass ejections that hit the Earth and produce aurora. But at Jupiter, we know that the magnetic field is tilted, again, by about 10 degrees. The magnetic field comes out of the north and into the south, and we've been observing it now for about 60 years, and we have seen some little shifts now with Juno, maybe shifting a little bit, but not flipping. There's no evidence of flipping at all, but we've only been looking for 60 years, so we'll have to keep looking. So what we see when we look up close is there's a big asymmetry between the north and the south. It's much stronger in the north than the south. We see some blobs that are stronger magnetic fields. And this movie shows you what the magnetic field lines look like. And you can see it's pretty much like a bar magnet, but it has some stronger regions and some weaker regions. That blue area, which they call the blue spot, which drives everybody bonkers because it's got not at all blue, but never mind. It's a weak magnetic field region. You can see that asymmetry. And that weak field region is actually very similar to what we have on Earth, the South Atlantic or South American anomaly that is now over Buenos Aires and has been changing with time. And indeed, at Jupiter, this blue spot has been drifting. We've just started to measure it to be drifting. Okay, so that's the magnetic field. Let's move up to the clouds. And what do we see in the clouds? Well, what we see, and historically, and I'm sure you've seen all this with your telescopes, the belts and zones. It's easier. Actually, you can see pretty much see a little bit of the belts and zones with just a good binoculars. And the Great Red Spot you can see with binoculars. But you can see that these winds, this has been observed with several spacecraft now, with strong winds going in alternate directions in the belts and zones. And we believe that this is driven by convection turning over and driving with the effects of the spin, the Coriolis force, causing east-west winds, with stuff rising and descending. Now, what's important is to think about the role of rotation of the planet on the planetary atmosphere. And it's nice to compare the Earth 24-hour spin period compared with a very slow planet like Venus, 243 days spinning, and Jupiter, which spins every 10 hours. And you can see with Venus, you see just one belt around the middle, whereas if we look at Earth and Jupiter, the Earth has 3 or 4 belts, north and south, equatorial belt going this way, and then the tropics going this way, and the Arctic and so on. And then with Jupiter, we've got multiple ones. Now with the Earth, you have to remember that the Earth also has continents which interfere with this flow, whereas Jupiter has faster rotation, more belts and zones, and more circulation cells, and it's much more stable atmosphere. Now we know this from looking at images with optical telescopes, but we can also use infrared and the Juno. This is the Juno instrument, but we've seen this from the Earth with infrared telescopes. You can see through the ammonia cloud at the very top, and you get sense of where it's dark is cold. It's very high up, And when it's bright, it's deeper down. You're looking deeper between the clouds and you're seeing where it's hot from inside. Now, if you just look at the infrared, you just see the outer layer. But if we could look with microwaves, we could look deeper down into the system. And so Juno is carrying this microwave system of 6 different channels, different wavelengths, different frequencies. And we can, with the longer wavelengths, we can look deeper inside and measure down to about 1,000 bar pressure what's going on in terms of the interior convection and distribution of material. So here is just a movie, orbit by orbit, showing you the ammonia concentration from these microwave measurements. And you can see that it's not the simple layers that we thought it was. There's a lot more vertical motion that's turning stuff over on these scales of several hundred kilometers, or you can see several up to 100 atmospheric pressures. So this was sort of not what we thought. It's not as simple as this simple cartoon that the textbooks were promoting. Now, what we think is going on, and this is a movie coming out of JPL, is that we have these multiple convection cells. So you have east and west winds, you have this turnover of rising and sinking flows. And you can see here, this is sort of what we think is happening for the outer layers. So what's going on deeper down? Well, we're not really very sure, but the current thinking is now that you have indeed this upper layer that produces the alternate east and west winds of the belts and zones. But if we look deeper down, what's underneath, maybe there's some interaction of the winds with the dynamo, but we think quite likely there's a deeper cell that's going on. And so there's more complexity of mixing up of ammonia and water. And then also there may be a much deeper convection cell underneath, multiple layers. Now, what about that camera? Well, here is Mike Levine, who built the camera for Mars, a couple of Mars missions. And what we decided was, okay, we want to put a camera to take some snaps for NASA. They always want to have images. But we thought, okay, it's hard to make measurements if you're going to be flying through the radiation belts, because your CCD detector gets just hit by the radiation. And so he's holding this camera, but it's actually really heavy because it's made out of tantalum, which is really heavy, in order to keep the radiation out. So it's about the size of a pretty big, SLR or something like that. And but it's strapped onto the spacecraft, and because the spacecraft's spinning, it takes some pictures. Click, 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 click. Comes around. Click, 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 click. Takes some more, and then sends them back. Now, what's so amazing about this is that these images are delivered to the website, and there's a link at the bottom. Just Google JunoCam or Mission Juno. You will see these images get published straight away. And then the public, citizens of science, pick up these photographs and do great stuff with it, okay? They process it. Here is an example, a really beautiful example where someone has taken the images and processed it. And here's a nice one Kevin Gill's done. And again, you can see this beautiful coloring, except this is probably a little close to natural. It's about the natural color with just a little exaggeration. It's another view. But the point is, because we're flying close over the clouds, under the radiation belts, we get lots of pictures of this beautiful structure in the atmosphere. And I don't think anybody really thought it would be this dynamic and structured. People crank up the contrast, crank up the colors. That's fine. You get to see more structure that way. Or they do art. Why not? Why not? Why not? It's fabulous. Just great. The creativity of the public is just huge. And so this has been, I think, a huge success in the fact that it isn't just half a dozen elite scientists who look at the pictures and go, ew, I think this is over here. Ew, let's have a look over here. It's just out for everybody to do what the heck they want with it, including some scientists who do some science with it. But you can see the level of complexity is just huge. Yes, why don't you ask your question and I'll repeat it.
Can you clarify the orbit of?
Yes.
Where is it doing perigeo
Right.
relative to the plane, where the sun
Yes.
is pointing and
Yeah.
we are and things like that?
Yes. Okay. The people online can see me because I can see the camera. You guys can see me. Let me try and do this. Say this is Jupiter. My fist is Jupiter. Okay. And then I'll put it over here. Okay. And then the spacecraft here. Oops. Let me do it this way. Okay. Oh, great. You've done a bigger view. The spacecraft comes in over the pole and it goes pole to pole in 2 hours. Okay. And then it goes all the way out and it was going out to about 100 times the radius of Jupiter in 50 and half of 53 days. And then it come back again and do another flyby. So go very quick over and then slow because of Newton's second law and then
Is
come
that
back again.
Point towards the sun or?
Okay, it started on approach. Remember that movie with the sun to the right? We were coming in on the dawn side, right? And you can see, so if you were looking at Jupiter, it would be on this side, okay? And that's when it started. But over 8 years, Jupiter has gone 3/4 of the way around the sun. And so that orbit has precessed effectively 3/4 of the way around Jupiter. Okay, and I'll show you a plot later. So that maybe gives you a sense of how the orbit
Would stay
works.
same in absolute space and changing where the sun is because it's.
Right. But there is this vertical precession due to the oblateness, the fatness at the equator, and fatter at the equator, more compressed at the poles by about 10%, similar to Saturn. Okay. Do you have a question or you? Okay. No. Okay. Okay. So here is another really cool picture. You can see these what we call pop-up clouds here. These are fresh ammonia clouds that are coming up. And over here on the right, I took this picture out of the window of a plane coming back from DC one day, because I wanted to show these are the sort of pop-up clouds that you see. You see them over Boulder, you see them over the east. Here at summer, this is just like the clouds that we have. And so this is an indication of fresh material coming up and condensing. At Earth, it's water. At Jupiter, it's ammonia. Now, we also flew over the poles for the first time. And this was the first time a spacecraft had taken a picture of the poles. Because remember, here at Earth, we only get to see the equator because Jupiter does not have much seasons. It's only a few degrees of the spin axis tilt. And so we don't see the poles from the Earth. So Hubble Space Telescope, the best telescopes that we've got at Earth, you can't see the poles. But you fly over, you can look down, and this is visible, and we get to see these vortices here in the pole. But it's actually much better viewed in the infrared. So the infrared camera of the North Pole, you can see we have 1, 2, 3, 4, 5, 6, 7, 8 vortices around the central vortex, okay? The South Pole, we have 1, 2, 3, 4, 5. Why do you have 8 in the north and 5 in the south? And it has stayed the same for 8 years. Who knows? Is it always that way? We don't know. Okay, so these are first things we've been observing. And what's kind of cool is here's a movie that just flips through orbit by orbit. And you can begin to see that there are some times when a little vortex tries to get its way in and it either gets absorbed by one of the other vortices or it gets spat out again. And you can see there is this change over time a little bit, but basically it stayed 5 at the south and 8 at the north. And the atmospheric scientists are having a lot of fun modeling this to try and find out what the heck's going on. So looking at Jupiter's atmosphere and the clouds with the infrared, the visible, the infrared, and the microwave are really giving us a sense of what's going on in terms of cloud dynamics of this very turbulent atmosphere. So then there's a great red spot, which I'm sure you're familiar. You can see it with a telescope. Voyager 1 flew by March 1979, Voyager 2 a little later. But it's been observed since the time of Cassini. Some people argue maybe even Galileo saw it, but Cassini certainly did in 1665. And he observed the spot, drawing these lovely pictures. And it was observed since. Photographers took pictures since 1965. The photography is easier, but actually I think the sketches look a little, a little clearer than these fuzzy pictures. But, now we flew by with Voyager. And I remember, I was a grad student. I just started working on Voyager. And I was about to get the data that was going to be my thesis work. And we looked at this and it was just like, whoa, look at this, look at this. And the next day it was on the top of the fold of the New York Times. Ooh, super success. Except it was in black and white because all newspapers were black and white back then. Okay, but totally cool. March 4th, 1979. So Voyager also was, because it was not a spinning spacecraft, it could stare at things. So it stared at the Great Red Spot, and you could see a 6-day circulation, this movie, and you can see it's about twice the size of the Earth. Exaggeration of the color is a little strong, but you can see, and the idea is that this is a high pressure region with Coriolis forces in the southern hemisphere. You get this motion. The Cassini flew by, and Caroline Porco made a better effort to try and get a better sense of the real colors. Voyager was a bit exaggerated, the coloring. But we really, struggling with what's the real color. So this is a Juno image that Bjorn Johnson has sort of argued this could be the real color. But what does real color mean? So let's talk about color of gases and how do you make color. So if you've got ultraviolet light coming in from the outside, it reacts with the atmosphere. Now, most of the atmosphere is hydrogen helium, but you've got in the upper layers ammonia, right? And so the idea is that if you have UV light hitting ammonia, maybe you could make aerosols that are colored, okay? And we do this in a lab. We think, well, if we add, so here's an example that you can see this, the brown cloud of Denver. Well, it's also Boulder, but we like to think that it's Denver, not as a pollution, not Boulder. Anyway, here's a picture I took last winter, looking out, and you can see this amazing brown cloud. And this is photochemical reactions happening in the atmosphere, pollution over the city. But when we think about Jupiter, we've got, what is this chromophore? What is the responsible for the color? And the idea was UV plus ammonium hydrosulfide, you'd make sulfides, and sulfur is yellow-ish, you'd make yellow, right? So they did the experiment in the JPL lab, and Bob Carlson found it was lime green, not what we expected. So, okay, let's do some other experiments. Say you add acetylene, and you make this thing that's got hydrogen, carbon, and nitrogen in various combinations. And what do you get? You get the right color. Voila, you get a sort of yellowy, orangey color. So it turns out we know this stuff. This is the yellow pigment on the roads, and it's the yellow ink in your inkjet, which is this stuff, combination of hydrogen, carbon, and nitrogen. So how do you make this at Jupiter? Well, this means you have to have ammonia coming from, not ammonia, you have to have acetylene, C2H2, coming from below, mixing up with the ammonia, and then you have it heated UV light on top, turning it into this mixture, right? And so this is called the creme brulee model because you've got the UV light making this colored stuff on the top. But how much of this chromophore do you need? Okay, well, I did an experiment at home. I took some food coloring and a glass of milk, okay? And you can see if you take a full glass of milk and you add 1 drop, 5 drops, and 10 drops of, food coloring, which you would use to color the icing on a cake or something like that, and you mix it up, and this is what you get. And I could then do the math, and I worked out this is 140 parts of ink per million parts of milk. Okay, a lot more milk than there is ink, as you can see. Middle one was 700 parts per million, and the one on the right is 1400 parts per million. Okay, remember that. So what do we have at Jupiter? We think that this chromophore, we have effectively 61 parts per billion, right? So very, very low concentration will produce the spectrum that's observed and produce this coloring of the outer layers. So it's not surprising it's hard to detect because it's very low concentration. But as you know, if you've made a coloring icing of a cake, you don't need very much to produce the color, okay? So how big is the Great Red Spot? Well, it depends a bit on how deep it is. We think it's somewhere between 300 kilometers and 1,000 kilometers. And so either way, it's really pretty thin. It's very much like a pancake. We think of it as being really deep, but actually it's much wider than it is deep. And it just covers, if you think of the size of Jupiter. Now, when we look at it, it's been changing over time. This is a Hubble picture, and you can see it's a lot redder than the time of Cassini, and it seems to have shrunk a little bit. What did Juno find? Woohoo! Okay, I love the artists. They're just so amazing. They're superb. Well, what Juno did find scientifically rather than artistically is that it's smaller. It's now more about 1.5 times the size of the Earth. Does seem a little darker. And we've now observed this amazing structure around it. It seems to generate this turbulent flow downstream. So the stuff goes past the red spot and then forms this wake, turbulent wake downstream. And indeed, the various citizen scientists do this fabulous job of mapping out the Great Red Spot and combining ground-based observations with space-based observations to map out the structure of the atmosphere and how it varies with time, the weather system. When we use the microwaves, we can look a bit deeper, and what we see, the structure seems to indicate some deep structure in the convection. So this is the picture that we think we have. That we have a complex structure with we have convergence below, rising warm cyclone going one way, and then as it goes higher, it cools off and spreads out and starts to go the other way, and then material descends on the sides down through the layers of cloud. So you can see this is a lot more complex than the original ideas of just a simple storm. A bit like the cyclones on Earth. And it is shrinking. We've seen it shrinking. This says at the bottom, the Great Red Spot. This is a public lecture I gave that you can find on YouTube. But you really need to come to the planetarium, Fisk Planetarium, and I do planetarium show on the topic. So it's kind of cool to see it all swirling around on the dome. But if you look at what's happened over time, Amy Simon has put together since 1880 these. Look at the diamonds, black diamonds, and then crosses. Over time, we can see it shrunk, and the Great Red Spot in length. Yes, if you put the scale of the Earth on top here, you can see it's gone from being nearly 3 Earth radii down to less about 1.5 over time. And then if you extrapolate forward, when is it going to disappear? Well, if it keeps shrinking at the current rate, it'll be several decades, or maybe it'll grow back. We have no idea. We don't know what's going to happen to it, you know. And we don't know why there's a great red spot in the south and not in the north. And why do you have this big storm that lasts for centuries? You know, could it be related to something that's underneath, like maybe in the dynamo flow that's been perturbed and sends up a vortex? You know, this is really getting people interested thinking about it. Yeah.
Why would the cyclone change its direction between the lower down and further up? Because like hurricanes don't do that.
Yes. Why is there this change in direction? Because hurricanes don't do this. It's because it's Jupiter, not the Earth. I think it has to do with convergence and expansion. I think that's the reason. And I think it has to do with the fact that rotation plays a really strong role in its behavior. This is from Lee Fletcher, who's an atmospheric scientist at Leicester University in England. Came from Oxford. That doesn't mean he's right. It could be wrong. That's the current theory, okay? If you got a better idea, write it up and publish it in Nature. Okay, so we talked a bit about orbits, and indeed we're sort of evolving the orbits. They're coming down, and we're now at orbit 62-ish, and you can see that it's tilting way down now, and we've reduced the orbital period from 54 to 32. And so, you know, with Kepler's second law, first law, which one? I've forgotten which it is. Which is the one that's the relationship between the orbital period and the orbital distance?
Pretty sure it's second.
Second. I thought it was faster in close and slower further out was the second.
It's the same thing.
Okay. No, it's not. It's to do with the semi-major axis and the orbital period. It's the third law. Right. Okay. Sorry. You can tell I haven't been teaching for 5 years. I've sort of forgotten the basics. Okay. But the important point is, because of this flattening and bulge at the equator causes this precession, we're now crossing at the equator as we come up over the equator and then over the poles and then down, and then we're moving that point where we cross the equator closer in, going past now the moons. Okay, and we can get pictures of the moons. So let's talk a little bit about the Galilean moons, Io, Europa, Ganymede, Callisto. And we've got for scale here, Mercury and our moon. And you can see that Io and Europa are a little bit bigger than our moon. Ganymede is about the same size as Mercury, and Callisto is a little tiny bit smaller. So tidal heating, if we look at the resonance of these three innermost moon, for one time that Ganymede goes around Jupiter, Europa goes around twice, and Io goes around 4 times. And so this orbital resonance leads to elliptical orbits, slightly elliptical orbits that lead to this tidal distortion, and it causes heating because you're sort of making it, distorting it. This heats it inside. And so what happens is that when we look at these moons, that Callisto and Ganymede are pretty much the same density, more or less 50-50 water and ice. Sorry, 50-50 ice and rock, 50% ice and rock, and a bit of metal. And we know there's metal inside Ganymede because it has its own magnetic field. It has its own dynamo. So there has to be liquid iron inside. But there's a lot of water too in that ocean inside Ganymede. Europa has lost nearly all of its water, except it still has equivalent of about 3 oceans, Earth oceans, in this big ocean underneath the ice, whereas Io has lost all of its water. And the tidal heating is driving a huge amount of volcanic activity on Io. The crustal flex of Io is 300 feet or so, plus or minus, so the size of the Statue of Liberty. So this is a really big effect. Now, when we flew by, we actually did not fly past Callisto, poor little Callisto. It's kind of boring. It's out there. It's just impact craters. Ganymede is the one that has its own magnetic field, and it has this mixture of rock and ice on the outer layer seem to suggest there's some sort of tectonic activity, different regions. Also has some impact craters that says that it's not super active in terms of geology because the impact craters accumulate over time. And this is another picture showing sort of the color, somewhat exaggerated color, but you get a sense of the structure. And this is a really amazing picture of this impact crater that Juno took, flying close and with really good cameras able to take this picture. Then we went on, and I'll say that JUICE, the European Space Agency mission, is on its way to Jupiter. It won't get there to 2031, but it will go into orbit around Ganymede and measure the magnetic field of Ganymede and the aurora and what it's like inside and the geology and all of these things, which will be very exciting to learn a lot more about Ganymede from the ESA JUICE mission. We flew past Europa with Juno and went to a region that was not well observed by Voyager and Galileo, and we saw these cracks that you can see, which may, presumably the tidal heating is causing this cracking of the ice layer. We don't know how thick the ice is. It could be anywhere between, say, 5 kilometers and 20 kilometers. There's big debate about how thick that ice layer is, but it's a lot to drill through. So what we hope is that some of these cracks are bringing up material from below, and by measuring the composition with the Europa mission that will fly by in the 2030s, measure the composition and maybe find a place like this sort of funny question mark thing where it could be the ice is a bit thinner and material is maybe able to escape out. This Juno images have just heightened the excitement about the Europa Clipper mission, which is due to launch in October 10th, I think is the date of this year, with a bit of luck. And it will try and work out what this brown gunk is. Could it be whale poop? And find out how thick the ice is and whether or not the water gets through to the surface. So that's the future. And Juno has just sort of added a bit more excitement to an exciting mission. Now, when it comes to Io, the innermost moon, it is just covered in these most amazing volcanoes. And these are Galileo mission images, which in between 1996 and 2003 took a whole bunch of pictures and observed changes in the surface. What you're seeing here is a lot of lava, which is black, spewing out invisible light. You're seeing sulfur, which produces these orangey red patches. And then the white stuff is sulfur dioxide frost. And that what's formed the evaporation of that SO2 frost causes the atmosphere. And we do actually have some plumes as observed by the Galileo mission on the side with venting sulfur dioxide and dust coming off. We see the dust in the visible light, but there's also sulfur dioxide coming out. And if you look at areas just a few months apart, you can see considerable changes. On the left, we have infrared light taken by the early missions. But this is what the Juno infrared camera is seeing, just covered in these erupting volcanoes. It doesn't even have to be up super close, and it's observed these different times. This is flying over the polar region, and you can see there's changes over time and just mapping out these amazing, they've mapped out at least 50 ones very carefully, but they're measuring at any one time about 100, 150 active volcanoes. And so on the flybys, there were 2 flybys in December and February, where we saw this amazing structure with the camera, really the highest resolution we've ever had. And because we were looking at the limb, the sun is over to the right, and on the left, what we're seeing is Jupiter shining, illuminating the dark side of Io. And then on the limb, where you tend to see a lot of structure. So if you look at the moon on the limb, you know that's the place to look for all of the vertical, the geology on the moon. You know, when you see a limb like this, it's also true with Io. You get to see these mountains sticking up, and these are sticking up sort of not quite as high as Everest, but almost on the order of a big, Rocky Mountains or Everest in scale. But they tend to be very isolated regions of rock that are sticking up. And then we have the volcanoes where we see, and this is in visible light, you see material that's flowing out, and in infrared you see hot lava on the surface. These are some plumes of eruption that we've seen with Juno, just flying by, taking a quick snap on the way. So that's all I have to say about Juno right now. We're hoping to extend. We think we're going to have 76 orbits, which will get us through to September of next year. We're talking and thinking and arguing with NASA, could we maybe plan another year after that? But the real big question is, as that orbit processes and we get into the radiation belt, will the spacecraft survive, or will those energetic particles just slam the computers and all of the workings of the spacecraft, and we won't be able to survive? We'll have to see. So far, things are going pretty good, all fingers and toes and legs, everything crossed, that it'll stay, but we'll have to play it by ear as we go. Thank you very much. Happy to take some questions. Okay, you can turn the light back up. Sorry. That was great that you turned it off, turn it down to see that movie.
Where is the red spot in relation to that not blue spot?
Yeah. No, the blue spot was the magnetic field anomaly, and the fact it says blue is purely a fakeness of choosing what color scale you use for your contour map. They could have chosen a completely different color and it would be a different color. So the color doesn't mean anything for the blue spot. It just means weak field region. The red spot, which you see with your own eyes, and this is what you would see if you were to look at it. If you were to look at this with your own eyes, this is what it would look like. That red spot is actually displaced. It's about a quarter of the way around. Yeah, probably not related, because even though the great red spot looks big, as I showed, it's very thin pancake-like. So it's really up at the top, and the blue spot in the magnetic field is much deeper down. Okay.
Are they both in the south?
Actually, no. The red spot is in the south, and the blue spot is in the north.
Thanks.
Okay.
Going after here to Steve Barr, and then till you'll find someone online.
Since we were just talking about Io, with all that volcanic activity, I would expect an atmosphere.
Yes, it has an atmosphere.
And how thick
SO2.
is that atmosphere?
Well, okay. It's a lot thinner than Earth's atmosphere.
Yes.
It's a lot thicker than the moon's atmosphere. And I believe it's thicker than Mars's atmosphere. Nah, you Martians. Sorry, I have a hard time with Martians.
That is thicker than I expected anyway.
Yeah, but the atmosphere, the Europa, Ganymede, and Callisto have very thin atmospheres. But Io has mostly, actually, it's concentrated at the equator, That happens to be where you have the sun hitting the frost, that frost evaporating, the SO2 frost evaporating to make an SO2 atmosphere. Yeah. Yeah. And I don't know the number of atmospheric pressures. I'm sorry. I should know.
I don't know if it's going to be a quick question, but over, I presume that near the core, all that hydrogen, since it's 20,000 degrees, is ionized.
Yes.
Okay, and the little bit of a follow-on question is, since we have heavy metals also at the core, okay, would there be enough free neutrons to cause any fission reactions?
My understanding is that there could be some fission reactions. Yeah, I would imagine that there's some radioactivity inside radioactive materials, but there's not a lot of radioactive materials. It's not like the Earth's mantle where you have a lot of stuff heating the Earth inside, and radioactivity is a big contributor for the Earth. For Jupiter, there's actually a lot less metal and a lot of hydrogen. Now, there's not enough pressure, even though there's 1,000 elephants with the bottom elephant standing on 1 foot side of a hill. That's still not enough pressure to cause fusion. So you don't have, you have to be, 20 times bigger than Jupiter to have nuclear reactions inside. But the heat that's on the inside comes from the fact that it is a big planet, 318 times the mass of the Earth. Now, you can think of Jupiter as being a big fat baked potato and the Earth being a pea, right? It's about the right ratio of sizes, more or less. And then you think about if you have a big hot potato on your plate and a pea, the pea cools off very quickly, the potato takes a long time. And that has to do with the surface area to mass ratio. And with a pea, it's got a lot of mass, a little amount of mass and a lot of area relative to the size, whereas with the hot potato and Jupiter, it's got a lot of mass and a relatively small area. Okay. And so it takes a long time for it to cool off.
Thank you.
Can I ask a question from the Zoom? You talked about the Galileo moons, but Jupiter has so many other moons and satellites. Can you comment on those as well?
Yes, and to be honest, I keep losing track of the total number. I think it's like 96, isn't it? Something like that, or 106, 90, some number. A lot of those are further out. They're really small. They're captured asteroids, and we didn't see them with Galileo. With Juno, the chances of seeing them with Juno are exceedingly small. But funny that you should mention it. We are now thinking, with our later orbits, you see it says Amalthea and Thebe here. Those are two of the smaller moons. And of course, they aren't just on one side. They orbit around and could be on this side. And depending on the timing, if we go, this goes into orbit 76, and we're thinking now, what if we could stay orbiting Jupiter for another year? Would we get a close flyby of Amalthea and Thebe? And we're looking at this. We're doing the calculations of the trajectory. So we might get to see Amalthea and Thebe. We'll see.
Do you have anything else online?
Yeah, Ron Rannick has his hand up.
Oh, thank you. Fran, wonderful presentation as always. Enjoyed it very much. Many of the folks who are in Denver Astronomical Society are aware that one of my other hobbies besides astronomy is ham radio. And in years past, I have used some of my shortwave radios to listen to radio emissions from Jupiter. And it sounds absolutely fascinating, up around 20 megahertz, 22 megahertz. And early in the discussion, you were talking about the synchrotron radiation around Jupiter. It's my understanding and recollection that that's a significant contributor to those RF emissions, but are there other processes at work that are also contributing?
Absolutely. And unfortunately, I cut this out because I couldn't talk about everything. But as Io goes around Jupiter, it throws out a ton a second of neutral material, SO2, sulfur dioxide. That material becomes ionized and it forms this donut of ionized material that's trapped in the magnetic field, sulfur and oxygen ionized material that goes around trapped in the magnetic field every 10 hours. And that bombards and hits Io. It also goes out and hits Europa, Ganymede, Callisto. But this is the work that my research area is the interest of how that plasma, that charged particle, sulfur and oxygen ions and electrons, is produced by Io and then is trapped in the magnetic field and goes around Jupiter, spreads out and so on. But it also drives an electrical current between Io and the planet, a wave. It's called an Alfvén wave, but it drives a current, a 1,000,000 amp electrical current that is carried between Io and the ionosphere of Jupiter. Now, back in 1966, a scientist at NCAR heard about this radio mission, which was being observed at Boulder by Jim Warwick and his group and George Dalk at the University of Colorado. And they were observing out on that hill just outside Boulder, north of Boulder. And then they went and took their telescopes up to Netherlands and made some observations up there. And what they noticed, and the NCAR guy said, oh, I want to test my correlation function by using the moons and compare it with your radio mission. Guess what he found? Every time Io was on one side of Jupiter or the other side of Jupiter, they saw radio emission. So what's happening is when Io is on one side of Jupiter, so Jupiter's behind me, you have radio emission being emitted in a hollow cone like this towards the Earth and all these other directions too. So they would observe it at Earth. And then Io would go around Jupiter to the other side, and they'd also see radio emission when it was on the other side. And we now know that this is in the decametric radio. So decametric means tens of meters, decametric, yes. So that's the frequencies. I think you said you were observing the megahertz, tens of megahertz, was it?
Around 22 megahertz. So the
Right.
wavelength is about 15 meters.
Right. Okay. So that emission comes from Io. It's triggered by Io, and you can see this. And you can buy a radio telescope, radio system, and put it up, a bunch of antennas. And I got my students to do this here in Boulder in our campus. And all we got was noise. All we could get was, it's just so much noise, radio noise from Boulder. We couldn't hear anything. But I do know that if you go out east or if you go north, people like yourself, amateur radio people, can hear Io's emission. Yeah, it's kind of cool.
Oh, yes, it is. I've got you on the mic here. I've got one other question. You mentioned the lava on Io. I assume that's basalt-like lava?
More or less. Yeah, I think it's more like the inner, the sort of deeper lava that comes from deep down than the superficial lava. So if you go to places where on the boundaries of where you have deep lava coming up from the Earth, yeah, it's similar to that, we think.
I have a question. You mentioned you had a polar orbit recently. Did you observe the sort of northern lights and the southern lights as well, auroras?
Yes. Okay, hang on a minute. I have to go into escape. Hang on a minute. I have some backup pictures.
Because of the magnetic
Yes.
Yeah.
Okay, I'll go to, this is the magnetic field, here. This is, I should have shown this. So this is EO driving this million amp current and the plasma going around. And what happens is that plasma gets heated, accelerated. This happens to be a movie from New Horizons that shows the eruption of Tvashtar, the plume on the northern pole of Io. And this is the Juno infrared emission. And then this is just telling you that you're dumping all this material into the system. But the net result is you charge particles, the charged particles get accelerated, they bombard the atmosphere of Jupiter. So they come from the region out in near the equator, near the orbits, and it gets accelerated along the magnetic field, just like the Earth's auroral particles come in and bombard the atmosphere, the North Pole and South Pole. This is a Hubble Space Telescope picture, and you can see the polar aurora. The main aurora is pretty uniform circle, but you see the footprints of Io over on the left. There's also footprints of Ganymede and Europa. The one of Callisto we haven't seen, but it might be buried in the main auroral oval. But here's a movie taken by Hubble, and you can really get a sense of the steady main emission, variable polar aurora, which we're trying to understand by flying over with Juno. And then this, not just a single footprint for Io, but actually the waves bounce back and forth and generate aurora for nearly all the way around Jupiter. So this has been very dramatic. And with Juno, we've been flying over, measuring the aurora, measuring the charged particles. So here is the aurora that you can see. The southern emission is very circular, the one here on the right. The northern one is irregular, it's like a kidney bean. Because of that magnetic field, anomaly causes a sort of distortion in the shape. And when you look in the infrared versus the UV, you see a lot more structure with the infrared. We're trying to put this all together and trying to understand the aurora at Jupiter and how it's all working and how it all comes together. So that's that. Thank you for asking that question.
Yeah,
Okay.
thank you very much. Thank you very much.
Now we'll take a question from a new person here in the room. And if you have a new person online, we'll go with that after this, Toby.
I have a question regarding orbit changes. Can you give us a sense, does that engine burn happen at a certain similar spot each time? Does it burn for 10 seconds or 10 minutes? How does that happen?
So the orbit perturbations, they tend to happen at, they do it at two places actually. One is out furthest from Jupiter and the other is when it's in close. They're very short. You don't need much of a burn to change the orbit. Or remember, if we're flying by the Galilean moons, you fly that close to Ganymede, you're going to change your orbit. And so there's also a change in the orbit due to flying past the moons. Okay, but it's a few minutes, not hours. Otherwise, it's just gravity floating. Spacecraft is just falling, around Jupiter.
Yeah.
Yeah, Ann was asking if you could talk a little bit about the spirals in the atmosphere and compare them to things in nature here on Earth that might be similar.
Oh, you mean the vortices? Well, we have vortices in the Earth's atmosphere. We have, tornadoes, we have cyclones, we have hurricanes, but they don't last very long, right? And that's partly because if they go anywhere near land, they dissipate. They don't keep going. You remove the water that is evaporating and then condensing and driving them. And the other thing is that because at Jupiter, it's not driven by water, it's driven by ammonia. And it's you're underneath, you don't have any land, you don't have mountains, you don't have continents. And so once you cause a vortex, it takes a while to dissipate. And so these North Pole and South Pole polar vortices, which we've observed for 8 years, right? Imagine a hurricane lasting for 8 years. They usually don't even last 8 days, let alone 8 years, right? And so at Jupiter, the energy is mostly coming from rotation, right? You're not getting energy from the sun in at the poles, right? And so you're somehow tapping into that huge angular momentum. Remember, Jupiter is 318 times the mass of the Earth, and it spins in 10 hours, not 24 hours, 10 hours. So this big thing has a huge amount of angular momentum. And so this drives a lot of what's going on in the atmosphere. The turbulence associated with the east-west driving turbulent interactions, and these vortices being produced that seem to keep going for a long time, right? Great red spot lasting for centuries, right? And so there must be less dissipation because they last a long time. They don't dissipate. And they seem to be tapping into this rotation. To be honest, I think the atmospheric scientists are still sort of scratching their head. I haven't seen a lot of really good models of this yet. We maybe we could take some of the energy of NCAR and get some of those computing capabilities that they have there to work on Jupiter. Would be good. Yeah.
I have a question. Are you gonna write a book?
Me? No. That's next generation.
Anybody else online? Anybody else here in the room? Okay, I guess that does it. Thank you so much.
Okay, pleasure.